Okay, welcome everybody. This is a little bit of extra help, hopefully, to get you through calculations involving calorimetry. It's the amount of energy required to change the temperature or change the phase of a substance. So, what we have here on the screen is a graph, hopefully somewhat similar to what you had when you completed the lab on Monday. You started out with a flat line, okay? Over time, the temperature didn't change, all right? And then as the ice melted, finally melted away, then as you continue to add energy, the temperature goes up. And then increases to a point, and then levels off again with a flat line, okay? I've labeled these line segments A, B, C, and D. So from A to B, okay, this is you're adding energy and it increases the potential energy of the ice, causing a phase change. So the solid molecules, they separate, they become a liquid. Okay, that's an increase in potential energy, and your ice is melting. Then from B to C, you can see the temperature steadily increases. Okay, that steady increase is called involves the specific heat capacity of water. And what's happening is the added energy is making the molecules move faster. They increase the kinetic energy. Then your temperature leveled off again and didn't change even though you continued to heat it. And this is another phase change. Involves vaporization, and the calculation involved is the latent heat of vaporization. And I've labeled that C to D. We didn't actually reach this part, but if you were eventually to vaporize all the water, the temperature of that steam would then go up. But we didn't actually see anything after D. A couple other pieces of information from this slide. Your numbers will be different, but I recorded a mass of an empty beaker as 60 grams and a mass of a beaker with ice is 105 grams. So the mass of the ice slash water would be 45.0 grams. For these calculations, we're going to assume that it was all ice and there was no liquid water at the start of the experiment. All right, so what we're going to do is we're going to calculate how much energy is required to take this ice at 0 degrees Celsius, this frozen ice, which is a solid, and vaporize it, so turn it all into steam. All right. The first step involves going from A to B. We need to use energy to increase the potential energy of the molecules and melt the ice. And that calculation looks like this. Hopefully, there we go. Okay, so from A to B is the energy needed to melt the ice. We have 45 grams of ice. Obviously, the more ice we have, the more energy is required to melt it, right? But in this case, we had 45 grams of ice, and every gram requires 333.6 joules of energy to melt it, all right? So a pretty simple calculation involving the factor label method. The energy required to melt it is 45 grams, 45.0 grams, times 333.6 joules per gram. And the factor label method, I have grams in the numerator and the denominator cancel out, and I'm left with joules. 15,012 joules are required to melt that ice. Now the lab asks you to convert to kilojoules, so there are 1,000 kilojoules in every joule, so 15,012 joules. Again, use the factor label method, joules in the numerator, joules in the denominator cancel out, and you'll be left with 15.012 kilojoules, or with the sig figs, 15.0 kilojoules of energy required to melt your ice. Okay, that's going from, looking back at this graph, from A to B. All right, if you need to, pause the video and go and complete that calculation for yours. Next, we want to look at this part, B to C. Okay, we're going to increase the temperature from the melting point up to the boiling point. And to do that, we need what's called the specific heat capacity of water. Okay, we have this same 45 grams of water. We have a temperature change from T2 to T1 is 100 degrees Celsius is the final temperature, and 0 degrees Celsius is the initial temperature. So the temperature change is 100 degrees Celsius. Now you may have different numbers for yours. Use your numbers. Don't use the 100. Use the numbers that you recorded. The specific heat capacity of liquid water is 4.20 joules per gram degrees Celsius. Means that every gram, to increase it 1 degree Celsius, requires 4.20 joules. So again, we use the factor label method. Okay, 45.0 grams times 4.20 joules per gram degree Celsius times 100 degrees Celsius gives you 18,900 joules of energy, or 18.9 kilojoules of energy. Okay, let's go back a minute. We've just found the energy required to take liquid water at its melting point and increase that temperature up to the boiling point. So now finally we need to do the energy required to vaporize that liquid water when it's at the boiling point. And that requires latent heat of vaporization. Okay, 45.0 grams, same mass of water, but this time to vaporize the water, you need a lot of energy to vaporize water. You need 2,260 joules for every gram that you need to vaporize when it's at the boiling point. So again, factor label method, 45.0 grams times 2,260 joules per gram gives you 101,700 joules, or again, just the unit conversion, 101.7 kilojoules are required to take that water that is at the boiling point right here and vaporize it to steam right here. Okay? Final step. So we have an energy from A to B, which melted our ice. We have an energy from B to C, which took the liquid water at 0 and increased it up to the liquid water at the melting point and increased it to the boiling point. And we have the energy from C to D, which is taking that liquid at the boiling point and vaporizing it. And so the final thing, the total energy added, we add those three values together, 15.0 kilojoules, 18.9 kilojoules, and 101.7 kilojoules to get 135.6 kilojoules. Okay, you'll probably have to go through and check stuff and add stuff. That's fine. Use the pause button. And if you need help, be sure to come for help. Hope things are going well, and we'll talk to you soon.